Okay, so looking at example 3.6, we're asked to write an expression for the entropy change when argon in a container at Ti and a constant pressure of P and at a volume Vi is allowed to expand to a final volume of Vf and is simultaneously heated to a final temperature of Tf. Right, so what are the initial things that we immediately see? Right, so we know we're working at constant pressure, so this is an isobaric process. We also can see we're working in a container with a specific amount of argon, so we know there's no change in the number of moles. And then we're given a bunch of information. So in other words, we have Ti, P, Vi, and N goes to Vf, Tf, P, and N. Right. Essentially, that's what we're giving at the beginning. And we want to calculate delta S. So I like to visualize these changes on a normal, well, you don't necessarily visualize it on a graph, but essentially what we have here. So our only changing variables are temperature and volume. So if we have a graph of temperature versus volume, then we have an initial point Ti and Vi, right? And it is expanded, it says expands, so in other words Vf and heated to Tf, so in other words Vf and Tf are larger than Vi and Ti. So in other words, it's some point up there, Vf would be and Tf would be, right? And because it's an isobaric process, it means we have an isobar that connects these 2 points. So in other words, we have something like that. Right, so how does this help us? Well, I don't know, perhaps you've read your textbook or looked at it a bit. There is a way or a method so we can break up this process, because of course we need to calculate the delta S for this process now. But it's difficult to calculate it for this isobar as it is, because this is a non-linear function at the moment. But we can do it if we break up this process into linear processes. In other words, 2 linear processes where we first look at a constant temperature process where we change the volume, and then look at a constant volume process where we look at the change in temperature. Right. So that's essentially, because those are 2 things that we've looked at before, actually. And I will tell you now exactly where we've looked at them before. We've looked at those 2 changes. So we've looked at the isothermal expansion of a gas in section 3.4.1. And then, of course, that just translates into the isochoric expansion of a gas, which is just the extension of that idea. In other words, just flipping around the volumes for temperatures. So you can use those 2 ideas together to calculate this. Right, remember isochoric means constant volume process, isothermal means constant temperature process. Right, and what we learned from those processes were that we could use a formula that says, let me just get my correct color, that says delta S is equal to NR ln of Vf over Vi. Right, so this is for the isothermal. Let me put that in another color. This is for the isothermal. Oh, that's interesting. Kind of like the moment. I'm going to just teach in that color from now on. Anyway, so that's for isothermal, and then basically we can just swap that. I will talk about the the isochoric process just now. Right. Okay, so that's for the isothermal part. So we're first looking at this bottom section here. So what do we need for that? Well, we see that we require N We have R and we have VF and VI. We know what that is, right? So how do we get Ni or N, the number of moles? Well, the number of moles, this is a perfect gas. So in other words, we can calculate the number of moles from the perfect gas equation. So we know that N is equal to VI, PI, or P, my apologies. It's just P over RTI. Right. And that actually remains constant, so it is what it is. So in other words, substituting this into that gives us then that delta S, should probably call this step 1. Is then equal to VI P RTI times R ln VF over VI. Right, and then you can just cancel the R's. So then we end up with VIP over TI ln of VF over VI. Right. So that is for our first step where we get that. Okay. Then if we look at equation 317, we get the equation that we require for the change in entropy for isochoric process. In other words, you know, when we're at a constant volume. So that is given to us as Cp ln of Tf over Ti. But of course, we're working with a constant volume process. In other words, this needs to be Cvm. And then when we're working with the molar, then we need to remember to include the number of moles here at the front. Okay, that's very important. All right, so what's the next question? So in other words, the next question is then we need to know what Cvm is, of course. And Cvm we can get from the equipartition theorem. So if you recall, the equipartition theorem gives us a way to calculate the internal energy of molecules, of atoms, or whatever. So the equipartition theorem says for a monoatomic particle or gas, it only has translational degrees of freedom. We do not have vibrational or rotational degrees of freedom. We only have the translational degrees of freedom. So in other words, the translational degrees of freedom implies it only has X, Y, and Z capacity. So that implies it has 3 degrees of freedom. So that implies molecularly, so number of moles wide. Oh, actually, so let's start a bit back. So per molecule, or in this case, per atomic argon, it means it has 3/2 kBt energy. Each atom of argon has that amount of energy. And of course, you need to multiply that by Avogadro's number. Then you get, so per mole, the internal energy is equal to 3/2 RT. Okay, and the relationship between Cvm and U is that the derivative of U to T is equal to Cvm. So if we just take the partial derivative of that, it means we have 3/2 R the partial of to the partial of T of just T, which is just 1, which is equal to 3/2 R. Okay, so that's how you get 3/2 R, if you just forgotten that. So we can write, this is just, maybe just highlight this as step 2. This is for step 2, yeah. So let me bring those two things down. So delta S step 2 I'm also going to substitute in our number of moles. So remember we have that n there at the front, so the number of moles is VIP over RTI. Then we have this 3 over 2R value, and we have ln VF, oh my word, TF over TI, and delta S step 1 is equal to, I've forgotten, VIP TI. Just ensure I don't translate anything incorrectly downwards, because then I'm going to make a mess of the next step. Okay, so we can just quickly rewrite this a bit. The r's will cancel, so then we're going to get 3 over 2 VIP over TI ln of TF over TI. Okay, and this one's already as what do you call it? Anyway, you know what I mean. Anyway, right. So now all that's left is the total entropy change. So in other words, delta S is equal to the sum of these two things. So step 1 plus step 2 is then equal to, I'm going to, okay, so let me write this out neatly, because that's the point of me doing these videos, is not to skip steps. VIP over TI ln of TF over TI plus VIP over TI ln VF over VI. Right. Let's take out this common factor. You see the VIP over the TI, so we left with VIP over TI gives us 3 over 2 ln of TF over TI plus ln of VF over VI. Right. And then we can use our law of logarithms. So if we have something in front of the logarithm, it can go to the power of that logarithm, or this natural logarithm. So in other words, it becomes VIP of TI then TF over TI to the power 3 over 2 plus then VF over VI. And also now the sum of two logarithms is the same as the product of the logarithm of the product of those two things in the sum. So we end up with VIP TI ln of, so let's first use this kind of brace. So you see that thing multiplied times that thing, the ln of that, all times that. Alright. So I think that gives you a nice explanation of where we got that from. Alright, so that's example 3.6. I hope me writing out everything gave you a better idea, especially perhaps, I think the most tricky part is perhaps this initial part, just analyzing how to get to the point of, you know, the two steps and whatnot. But you can always do that. So if you see different parameters changing at the same time, then it generally means that that's how you're going to go about solving this kind of problem. You first keep the one constant and then keep the second one constant while you change the other, and you just sum the difference. Okay.